Hello again, everyone. This is Mr. V. Hill. Today we're going to talk a little bit about the parent functions, and specifically for the three types of functions that we're going to be looking at in Algebra 1 this year. But before we get into that, I want to tie this back into what we've already been doing for a while now. So first, we just want to recall what we did with arithmetic sequences. So first, let's just look at a little example here. Let's try this one. 5, 8, 11, 14, and so on and so forth. So we're starting with 5 and we're adding on 3 each time. And we won't go through the whole thing, but hopefully you have developed enough understanding by now that you know that you can get the nth term in this sequence simply by taking the starting value 5, and we're going to add on what we're adding each time times the stage number n. Or if you want to rewrite it this way, just switching the order of the terms, 3 times n plus 5. And again, this is where we were starting with, this is the 0th term. So here is a sub n is equal to 3n plus 5, where n is any whole number. We could have done it just as easily, just letting this be the first stage and letting n be any natural number, but I don't know, I kind of like this way just because it leads into what we're going to be doing next here. And the next thing we're going to be looking at is a little thing called linear functions. And the thing about linear functions is that they're basically the exact same thing as arithmetic sequences, except here with the sequence, the actual term is dependent upon the stage number. So the stage number is your independent variable, and the term is the dependent variable. And so n is referring to any whole number or possibly any natural number, but now we want to let the same kind of thing happen, but now instead of letting n be just 0, 1, 2, 3, 4, 5, we want it to be everything, meaning all the negatives, all the fractions of integers, and all of the weird irrational numbers too, meaning any real number. So now we're going to change this up, and so instead of using n for our variable, we're going to use x. And instead of a sub n as the dependent variable, we're going to use y. So we can rewrite this equation here as y is equal to 3 times x plus 5, and now x isn't going to be just a whole number. This is where x is any real number, meaning anything on the number line. Okay. So, in general, linear functions have a basic, they look like this essentially. We've got a number times x plus some other number. So we just have y is equal to some number a times x plus b. And so actually what you've probably already seen before is instead of using an a for this number that x is being multiplied by, you use m. So we could just as easily say y is equal to m times x plus b. It doesn't really matter at all. All we're saying is that y is always going to be equal to some number times the variable x plus some other number. Whether you call it m or a, it makes no difference. So anyway, linear functions are really just arithmetic sequences, but now we're letting this n thing, now calling it x, and now it's going to be any real number, not just any whole number or natural number. Okay. Now, with these functions, we have what is called a parent function. And so we need to define that. And a parent function, well, all that is, it's, in some weird way, it's the, put this in quotes because it's, the semantics gets a little goofy, but it's kind of the simplest version or simplest example of a certain type of function. And so for linears, the parent function is y equals x. Okay, so basically that just means that the number that you're multiplying x by is going to be 1, and the number that you're adding on is 0. So it really does fit into this form here. Y is equal to 1 times x plus 0, but you don't need to write the 1 or the adding 0 on there because it doesn't do anything. So that's the parent function for linears. It's the simplest version. And if you want to see what that looks like, well, maybe you should already have an idea here, but if we just type this in, y is equal to x, and we want to graph that thing, oh wow, it's a nice straight line. And even though this window is skewed here a little bit, what you might see if you look at a table is just that the x values and the y values are always the same thing. So if you want to graph this thing, all it turns out to be, I'm just going to do a quick sketch here, x-axis, y-axis. These are going to be points like 0, 0, 1, 1, 2, 2, 3, 3, negative 1, and so on and so forth. You see it's a nice straight line going at a 45-degree angle right down in between the two axes in the first quadrant and the third quadrant. And that's the parent function for linears. And what we're going to see in the next activity is that we take this parent function, and as we change these numbers here, a and b, that's going to change the way the graph looks. And we're going to quickly understand how those numbers are going to affect the graph. So don't even really have to think about it or graph it. We can just look at the equation and know what it's going to look like just by the equation itself. So that's linear functions. The next one we're going to look at, instead of going over to geometric sequences, I'm going to take a moment and just look at quadratic sequences. So we'll recall those too. And using an example from that tiles activity that we did, the first pattern that we had there was formed with this 3, 8, 15, 24, and so on and so forth. And if you went through all that, what you would have figured out is that the general rule for the term number, a sub n, what's that equal to is n squared plus 2n. Or it's n times n plus 2. First term, looking at this is the first term, 1 times 3, 2 times 4, 3 times 5, 4 times 6, so on and so forth. So it's not too bad. When you simplify that, we get this. And that's where, in this case, n is any natural number. Okay. So, switching up from a sequence to a function of the real numbers now, these things have the exact same name, quadratic functions. We could just rewrite this as y is equal to x squared plus 2x, now where x is any real number. And we could graph this and all that, but I want to focus on the more general case. And so in general, quadratic functions look like this. Y is equal to some number a times x squared plus some number b times x plus some number c. And so the simplest version of this quadratic function here, the parent function, well, the simplest one is y is equal to just x squared. Don't even have anything here. This is called a linear term. This is a constant term. But basically what we're meaning here is that the a is 1, the b is 0, and the c is also 0. And when we graph this, let's just put a little squaring on that x. We'll graph it, and we see this nice little U shape. Okay, and we'll look more into that when we do this next activity. But that's the parent function here. Sketch this out, x and y. All it is this nice little U shape, which is really nice and symmetric about the y-axis. And we'll look more into why that is as we go along. And this is y is equal to x squared. And this shape for quadratics has a special name. This thing is called a parabola. And we'll be working with parabolas a heck of a lot this year. Anyways, that's the parent function for quadratics. Now, moving on to the geometric sequences. So let's recall that really quick. And we'll look at maybe this example here of start again with 5. So then we'll go to 15, 45, 135, and so on and so forth. So we're just multiplying by 3 each time. And hope you remember that the general rule for a sequence like this, we would just take a sub 0, 5, and we're always going to be multiplying by the common ratio of 3. So that's raised to the nth power. Again, now this in this case where n is any whole number. Now, when we extend this out and replace this with an x that's going to be any real number, we call these things now exponential functions. And so the dependent variable instead of the term is now y, and we have 5 times 3 to the power of x, where x is any real number. And you might ask yourself, well, wait a second, if we're taking any real number, like say, I don't know, 4/7, how in the world can you raise some number to a power of 4/7? Well, there's some tricks there. But we can do it, and we'll explain more as we go along, looking into how that really does work. But that's for another time. In general, these exponential functions are going to look like this. I'm going to take y, and that's going to be equal to some number a coefficient like that, times some number b, the base of the exponential, raised to the power of x, and then plus maybe some other number c. But for exponentials, the parent function is, and I'm going to lie to you for just a moment here and say that the parent function is y equals 2 to the power of x. Basically saying that this coefficient out here, a, equals 1, the base of the exponential is 2, and what we're adding on is going to be 0. And for our purposes, this will work. It's not really the case, because you can let the base be anything you want, really, well, except for a negative. And we'll talk about why in a while. But really, just as a little aside, so I don't completely lie to you, the parent function is y equals e to the power of x, where e is Euler's number. and it's got a really nice definition, but it's a really fantastic number. It's transcendental, like pi. It's about 2.7 something, but you'll see more of this as we go along. You'll definitely look at this a lot more in Algebra 2. And so if we want to look at just the easier version with a base of 2, not this crazy number e, we can graph that pretty easily. Clear that out. And we'll just go y is equal to 2 to the power of x. And we'll graph that thing. And there we go. So notice we've got this curve going this way, and it does keep going this way, and actually it looks like it stops, but actually it just keeps getting closer and closer and closer to this x-axis. So you do a quick little sketch of it, x, y, and we'll investigate these a lot more as we're doing our next activity with graphing a whole bunch of stuff. But basically, the curve shoots off really steep that way, and then just over here just keeps getting closer and closer and closer to the x-axis. It won't ever cross it and become negative. Okay, well, that's the basics of parent functions, and we'll talk about these and different versions of these kinds of functions a lot more in class. Oh yeah, we already started that one activity, so we'll do some more tomorrow. All right, see you in class.